Good morning, everyone. I just had this urge to do like a "Yo, what's up?" and like all the things that the streamers do. Um, Before we start, make sure you like, comment, and subscribe. Here's a message from our sponsors. Blah 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 blah. No, okay, we're not going to do anything like that. Although I do enjoy the idea that we're in. Yeah, that's it, Sean. Hey, it's your boy. I do enjoy the idea that we are in this kind of weird transitional world in between the stereotypical view of what a university lecture may have been in the past. There's someone up at a lectern and all these people sitting there being perfectly silent while this person speaks, and we're moving into this newer world where all the little conversations that could happen in a lecture theatre that can't because everyone needs to make noise with their voices to talk like that can actually happen in chat. And what I've been seeing from that over the past 2 terms, this is the 3rd term of doing it this way, is that conversation in chat seems to be superior to trying to interrupt a lecturer to ask questions. Like, I think that's I don't know about you, but I think the idea of sitting in a room of like 500 people and sticking your hand up to get attention is just a little bit freaky. So I do like the fact that we can chat and you can have a full-blown conversation going on in the chat there, and it doesn't interrupt what I'm doing, and it doesn't interrupt what people get to hear of the lecture. Especially because you go like, what did he say? I was reading chat. I'll just roll back 10 minutes, play it at double speed, and I'll be caught up in a second anyway. You know. So there's all these like this quality of life stuff which I find quite nice. Yeah, people are saying that there, people are agreeing in chat, which is nice. And you can do that. You don't have to like interrupt me in like if we were in a Zoom call now and you'd be like speaking over me, really, that would be weird. Or in a lecture theatre would also be weird. Yeah, I don't know. Just a little anecdote as we're winding up the lecture for today. Starting up the lecture. Winding up means ending. Anyway. Couple of things I wanted to mention this morning before we fully kick off what I'm going to talk about formally today is the assignment is in full swing. You are now potentially in the middle of your assignments. Some of you super keen beans have already finished the assignment. Some of you have not started the assignment, but I hope that everyone, especially if you haven't started the assignment yet, you've at least looked at the assignment spec, because I think it's worth, even if you haven't started typing and coding for the assignment, your brain, your subconscious can do a whole lot of work on it if all you do is read what parts of the problem are and then let your brain just kind of simmer on it for a while. If you've got other assignments to do, you've got other more urgent deadlines to take on, that's fine. But it's nice to have it just bouncing around in your subconscious, because you'll find that solving questions will be easier if you have kind of pre-thought about things like that. I'm always reminded of this proverb around now when I'm talking about people and trying to convince them to start the assignment as soon as they can, is an old proverb which says, the best time to plant a tree is 50 years ago. And the second best time is now. So I think what they're trying to say with that proverb is that, yes, okay, in a perfect world, we were prepared ages ago, and we started the assignment the second it came out last week, and we're well on our way into it, and we're happy with what we're doing. But if we're not, that's okay. We can still make the best of the time that we have now and say, all right, so we didn't do all that preparation. We didn't do all the amazing stuff that would be the optimal way of doing things. That doesn't mean we give up on where we are. It doesn't mean we've failed or anything like that. It means now is the good time to start. And that's good advice even up to, and to be entirely honest, it's good advice even after the deadline. You've got a little bit of time after the deadline where we have a late penalty, and if you haven't started the assignment yet after the deadline, I still encourage you to start it. It's not over. There's reason to be maybe a little stressed at that point, but there's no reason to panic. You can still pass the assignment. if you are in those dire circumstances and you just sort of sat on it and left it until late, if you do it, you're still going to get some marks for it. So it's still probably worth doing. And even if you don't get any marks for the first assignment, it's still worth doing, because the feedback that you'll get from the tutors and the experience of doing it is going to give you more marks in the second assignment and the exam and things like that. That's if marks is the only thing you're after. If you're after learning about how to program, which I think is what a lot of people are here for, then it really doesn't matter whether you get marks or not. It matters whether you do it and whether you get that experience. Let's see, whatever. Yeah, Alex is saying Slido. Yeah, I use Slido at one point in the live lectures. I'm wondering if I'll hit a point where we can go back into campus and I'll do live lectures that are also live streamed. So I'll be there lecturing in front of everyone, and I'll have like the whole camera rig and the microphone and everything there, and that thing's going out live at the same time. I think that could be quite interesting. I won't know where to look. I'll be looking at the camera and then I'll be looking at people and stuff like that. The other funny tidbit of that proverb about when to plant a tree. I'm pretty sure it's an ancient Chinese proverb, but I learned it from World of Warcraft. Thank you, the Mists of Pandaria expansion, for having little tidbits of Chinese lore in there, which is great. Okay, let's launch into the lecture itself today. So, a little bit about what we did last week. So, we consolidated some of our knowledge about functions and arrays last week by expanding. People are talking about playing World of Warcraft. I just want to say I'm so glad that World of Warcraft released after my degree was finished. So that was important, because then I actually completed my engineering degree back in the day. Otherwise there would have been problems. Okay, so we were learning, continuing our learning on functions and arrays, adding on to functions the fact that we could use libraries, so whole other files worth of functions that we can import from the C standard library. And that means that there's a lot of stuff that other people have written that we could use. Things to remember about that are that there are lots of them, and you don't necessarily need to know all of them. Some of them will come in handy. The hardest thing, and it comes with time and practice and sort of continual learning, is which ones of these are useful to me and how do I find them. So often looking up reference for things is very important. Sometimes even just Googling the ideas around solving certain problems might give you some information on what libraries people suggest to use for them. We expanded our arrays into 2D arrays and did the little tourist program, which someone commented on the YouTube video. It was a great comment. It was like, can we use this to make Pac-Man? And I was like, shut up, that's a future assignment idea. Well, it's not now, is it? But it could have been. Yeah. So I think I thought that was a great comment, because like that 2D grid and moving stuff around, there's actually a lot of, especially old school computer games, that you could definitely start to think about how they were actually made. Like look at like the very, very first Legend of Zelda. It's definitely a top-down grid with these little images that move around and stuff. Yeah, Tom, right? Exactly. It's like when a great idea comes up with like the whole class sees it, I'm just like, oh, I can't use it now. It's not going to be a surprise. But maybe next time's class won't know. And then we looked at pointers and memory addressing and stuff like that. So this was our first look at using memory. I'm going to let that simmer in your minds for a little while. And we're going to use it in more depth later. So after we've kind of had a go with it in tutorials this week and had some kind of, I guess, demonstrations of how they work, this week's content's actually going back to some other things, using other variable types and stuff like that. But we will definitely be coming back to pointers. I just wanted to plant the idea in your mind and let it simmer for a while, so that in a couple of weeks, then when we get back, we can we can start working on them and using them in earnest. I should say, when I'm saying get back like that, it should be a reminder to let everyone know that next week is going to be what's known as Flexibility Week at UNSW. It's the idea of a midterm break, in a sense, where week 6 has a particular kind of gap where we won't have any deliverables due during the week and we won't have any compulsory activities during the week. So the weekly test that we're going to release this week won't be due next week. It'll be due in week 7. There will be no tutorials and labs, and the lectures will be optional. I'll be covering content that's not necessarily course content. So what I might do, I haven't decided whether I'm going to do 1 or 2. I will definitely do 1 live stream where I talk about things that are not accessible course content, but kind of important in terms of, like, you know, thinking about how you want to carry yourself as a professional. So I don't know if those of you who are later in your degrees and doing this as an elective or a gen ed, that might be very interesting. Those of you who are, say, first year students, it's still kind of interesting to look at, because it's a talk where I just go into, like, information that I've gathered over the years about what people are hiring for and how we can get ourselves there, that kind of thing. Anyway, I don't want to talk too much about that, because we don't need to. You don't need an intro to that. You can always just come to the lecture next week if you want. I will let you know the schedule for what's happening next week in my next weekly notice. I didn't want to say too much about it in the recent weekly notice, because then I knew that was going to throw some people off, and then they wouldn't come to lectures this week and miss something important. Okay, so today, what are we looking at? We're going to start with a little bit of a recap of pointers, and then we're going to look into this process called debugging. And I think that this is a good point to talk about this, because we are right now getting into writing code for our assignments, and writing code for our assignments means that we're now creating stuff that we don't understand. So you have a good chance, a decent chance with a lot of your lab work to create code that you inherently understand, because you spend like an hour or 2 on it, or even more. Some people spend more, especially on challenge exercises and stuff like that. But you're looking at one topic at a time, and then you can sit down in one session and finish one lab exercise. So you don't necessarily give yourself enough time to forget what you've done. The assignment, it's nearly inevitable that happens. By the time you get to a later stage, let's say you're pushing through to stage 4, stage 1 is going to be like this foggy, distant past. And if there's an error, that later stages happen to open up in the earlier stages. So there's something wrong with the earlier stage, but the consequences of it can't be felt until you try to do a later stage and reuse some of the stuff from it. You don't necessarily know what's going wrong. So what I want to go through today is a process through which we identify errors and solve them. And I'm going to give you a few tricks. I mean, I'm going to show you a simple example, which means some of you are going to be able to look at it and go, I already know what's wrong with that. But what I'm going to try to show you is what to do when you don't know what is wrong. So some kind of tried and true techniques that we can use to pick apart our code, find out exactly which bit of it isn't working, and then fix it. Zeal Liang, I'm sorry, I can't read everything that you're typing there, unfortunately, but I think that what you're asking about is what is a bug, and we will talk about that definitely, because a bug is a type of software error, but we're going to go into that in detail. After that, we're going to introduce the thing that we're doing for like the whole of this week, in a sense, which is characters and strings. So we're going to start off with characters, which is single letter variables. So now we're expanding our variables from numbers to letters. So we spent plenty of time with numbers, but the time we spent with numbers was not really about learning about using numbers in programming. It was more about learning how to use loops and arrays. And now we're going to start adding different variables that represent letters instead of numbers. And then on Friday, we're going to add in what we call strings, which is arrays of letters, and how we use them as well. So, quick recap of pointers, because I think pointers is something that definitely needs more than one look before people really get the idea of what's going on. So, recall that a pointer is a variable. So, like any integer or any double, or an array, it has a space in memory somewhere where it stores information. The trick behind the pointer, as opposed to other variable types, is it doesn't just store a value that the human cares about. It stores a location of another variable, and that is a memory address. And the memory address is actually a number, so you could nearly think of a pointer as being a complicated form of integer. It stores a number that gives it access to something else, but not just a number. It also stores what type of variable it's intending to look at. So pointers, the name will remind us a little bit about what's going on, because a pointer points at something. So it's a variable that says that other variable, that's the thing that I point at. And so it'll keep track of another variable like that. And we use them a lot so that we can pass around information about things. And as we get deeper into using pointers, we're actually going to use pointers to kind of like I don't know if anyone's ever gone on a treasure hunt, or like this old school pirate treasure thing. This idea of I'm here and there's a pointer that tells me to go over there. And I go, okay, cool. Follow the pointer. Go over there. And then when I get there, I open thing, go, is it the treasure? It's not the treasure. But there's another pointer. And the pointer goes over there. And then we'll follow that one. And you can actually follow a trail of pointers through different parts of your memory. And we're going to look at that later. We're not going to look at that this week. We're going to look at that after the break. And we're going to learn how to start building up what we call data structures. So a structure in memory of things that are connected together that allows us to do more than what we've been able to do with individual variables and stuff like that. So we'll see when we get there, though. But that's where pointers are going. So the actual syntax of using the pointers, the star is the symbol of the pointer. Same way we had the square brackets being the symbol of the array. So anytime we have a star, apart from multiplication, so this is another reason why we have white space between operators. So when we have the star, we know that the star, if it's just there and it's sort of connected to the variable, C syntactically won't mind whether you do or don't do that. But we do it so that we know the difference. So when we have the star connected to the variable, if it's a declaration, so if it has a type before it, that means we're creating the variable, then we're creating a pointer. After that, if we put the star next to something, it means we're using the pointer as something that aims at another variable. When we want to know where a variable is, we can ask what is the address of a variable, and we address a variable using the AND. So this is our way of saying, if I was to put I here, I would be saying store the value of I in this pointer. So this pointer would then be created, pointed at memory location 100. And we don't even know what's at memory location 100, so that might be quite dangerous. As opposed to me saying the AND of I says, I want to find out where I is, and then point this new pointer at the location of I, which this means whatever address I is in, which we don't necessarily know, but we know that this pointer now points at this variable, which is good. So that way we can then get access to that variable as we need. MX is asking if the whole point of pointers is just to change things in a function back into the main function. And asking whether that's all it is, and it's just to make those cleaner. And hopefully I've already answered your question when I was talking about the idea of pointers being this chain of locations in memory where each pointer points at another location that has a pointer in it and another. I'm not going to talk too much about that yet because it's quite complicated. I'm going to set up that in a whole, like a series of lectures in week 7 onwards that are going to talk about that. But you'll see that pointers, what we've got now of pointers is just sort of scratching the surface of what they're capable of doing. They're giving us direct access to memory, which can be super useful. So Josh is asking, could you have 2 variables, one named I and one named star I? Unfortunately not. The variable name of this pointer is IP, rather than being star IP. So later on, if I use IP, let me go to the next slide. I love it when your questions lead me to the next slide. It means that we're all on the same path. When I have IP, then there's 2 ways I can use it. One here is the address, which is the value of the pointer. So the value stored in the pointer is the address of another variable. And then if I use the star on that pointer variable, that's me following that pointer to where it was aiming and saying, okay, what is the value in that other variable that I'm aimed at? So, actually, you know what I'm going to do? One day I should do a diagram example in CS Paint. That would take me so long. Okay, draw one individual line and then another. Okay, so here's my pointer IP. And then somewhere else, we've got the variable I. And in memory, this is 0x. Remember the 0x notation for hexadecimal numbers that I showed? So this is 0x, 0B6. I'm just entirely making up that address. I don't know if it's definitely correct or not. And the number 100 is in there. So the thing that the IP stores is actually 0xOB6. And because it stores 0xOB6, that's the thing that's linking it to here, that's saying I aim at this memory location because I have this memory location as the value that I store. And so it's in there. So if I was to read, let me just change cursor so you can see what I'm pointing at. If I was to read the value of IP, the value of IP is 0xB6. But if I say star IP says, I don't need this value. I want you to use this value to get to here and then read this value. So IP's value is 0x0B. Yeah, that's a B. My mouse slipped. 0B6, but star IP. You could nearly think of the star being this arrow, and this arrow doesn't exist in memory or anything like this. This arrow is nearly an action that I took to give you the idea of this, the idea of this pointer being connected to this, where in our computer this arrow doesn't exist. You know, it only has this, which says which memory address it's looking at, and it has this, which is that actual memory address somewhere else in memory. So we're just in our computer's memory here. But if we think about it like that, star IP says, okay, we would use this imaginary arrow to get to here, and then we get the number 100 out of that. People are asking about the AND, so let's continue this little thing here and say I sits at the address 0xB6. So the AND of I is not the number that it stores, but it is the address that it stores. So that's 0x. Sorry, not the address that it stores, the address that it's at. 06OB6. 0xOB6, which is the address there. So these things are all of the different kind of syntaxes that we can use around pointers. So note that the AND of I is a memory address. The pointer value is a memory address. So what we get is this interchangeability between these two things, where this is a value, which is a memory, and this stores a value, which is a memory, which means that anytime I want to use one of these, the value of a pointer or the address of a variable, they're interchangeable. So I can have a function that is saying, give me a pointer, and I can give it memory addresses, and it will accept it. Likewise, if I have a function that, I can't even say, because a memory address is not a type, it's a value, so I can't say that there's a function that should take memory addresses. So the only type that I have where I could put this kind of number in is a pointer type. But either way, these will go back and forth like this, in the same way that typing in raw numbers in my code is the same as saying this is a value that could be stored in an integer. So I did a little example of that as well at the end of lectures. Would it be lecture 7 or lecture 6. I can't remember, but I remember doing something like that. So whichever lecture we were talking about pointers, I went back and showed a little bit about variable types and how they work in functions and things like that. Yeah, so a couple of questions there. People are asking stuff like David saying, so is star is like go here, do this, and is like look up this and write down the address. That's perfect, David. That's a perfect way to think about it. That'll be really really handy when you say it to yourself like that. It'll come through really nicely. I think that one of the biggest difficulties with learning about pointers in C is just all of these like single letter like things, and it's just like it's all just like these weird symbols, and it's much easier to get thrown off by weird symbols than it is to like use words. Like I find the way that they do if and while loops and stuff like that to be much easier to teach and to learn than pointers. So if this was the word address, then you'd all be like, oh yeah, it's easy, it's the address. And if this was like lookup or something, it's actually called dereferencing. So this is a reference to this, and to dereference is to take it to where it's supposed to be and grab the value. But it's just one little step of the memorization. I think there's probably more difficulty in pointers in terms of like learning why they exist and how to use them once you get over this sort of syntax here. Okay. I'm kind of glad I jumped out to draw that, because I think that you can learn more from me drawing that than me talking about the slides here. You can always go back over the slides later. Okay, so we talked about different ways of accessing and the address and things like that. The other thing that we have as a possibility is now we have the possibility to use multiple variables in a function and to use variables that exist in other places in the function. So when we are running a function like this one, where we're putting pointers into the function, that means we're giving memory addresses to the function, which means that the function doesn't create the variables that it's aimed at. It only creates new pointers that are aimed at the same things that the rest of the program gave to this swap nums here. And so this is something we used last week in the shuffler. So these two memory addresses are memory addresses of variables that already exist somewhere else in our code, which means this function now has the ability to change other things in our code. And we also had a closer look at arrays and noticed that arrays are actually like these memory addresses. So when you pass an array into a function, the address of the array is what goes into the function. I love it when I do that. I talk about the next slide on the previous slide instead. But yes, so pointers and arrays, very similar in that the array variable, so if we don't use any square brackets, we just use the whole array on its own, we will get the address of the start of the array. How is my stream going at the moment? I'm getting not quite as much upstream rate from my computer as I should normally have. I hope it's okay. I mean, it's like, it's maintaining that it's like at least 4,000 or 5,000 kilobytes a second, but it's not keeping up the full 8,000 that it usually is. Hopefully, if you're a little bit behind, it'll catch up on its own. All right, seems to be evening out. Okay, so things that I wanted to talk about today. So I thought it was important at least to spend 20 minutes, half an hour on pointers again, because the way that we learn something difficult like pointers is to see multiple different perspectives of it over time, and then it should be able to stick in your memory. So now we're going to talk a bit about debugging, and I remember something about there was a primer for students going into university for the first time, and all the things that you would need to know about, because you would need to learn references from people who were approximately 20 to 30 years older than you. So this is an example of one of them. If any of you know this, then thank you for knowing this, because this is probably one of my favorite movies of all time. This meme is from the movie Aliens, and this is an actual quote from it. So I say we take off and nuke the entire site from orbit. It's the only way to be sure. So that's that's a little joke on what it's like to remove bugs from a computer program. So a bug is a really, really old term. Thank you, Jamie. The bug. That's another line from the movie. This movie has so many quotable lines in it, and I'm not going to. I was about to talk about all these kinds of amazing things in the film, and then we'll burn all the lecture time. So, a bug is a name for errors in software. It comes from way, way back in the 80s, where people used to use, instead of code that we type on a computer, they'd actually have cards, and they were called punch cards. And they would have holes punched them in different places. And that's nearly like having bits switched on and off in different places. And they were lined up in these pieces of cardboard. And the cardboard was fed into a machine that would read where the holes were in the cards one at a time. So you imagine the bandwidth you're getting on that. It's like super, super low. And back then, having bytes worth of data was amazing, right? So at that point, when they had computer errors or software errors, they came up with the idea that what would happen if there was a bug sitting on the card when it went into the machine. The bug might block one of the holes. I don't know if that's exactly the story, but it's that kind of idea. And so they talked about it like that. Like, maybe there was a bug that got into the machine, and that's why the software didn't work. And somehow that term of a bug in the code has continued right on through until the present day. And so we talk about the idea of a bug in the code, and then we talk about the idea of debugging, which is an entirely made up word, right? But it's the idea of removing these bugs from the code. And so I think everyone at this point in the course, everyone who's been working on all the labs and tutes and stuff, has definitely seen bugs in their code. So you've seen times where you write stuff in, and then when you compile it, oh, Tom thinks 40. Oh, no, it has to be 40s. Yeah, 80s we had all digital computers. If I'm talking punch cards, yeah, we're talking 40s, 50s, around that era. So yeah, we are thinking about Grace Hopper era. Is Grace Hopper's who I'm thinking of, right? Grace Hopper is the one who was working on building up towards the Apollo program, the moon landing and stuff like that. 1947, Tom's looking up in the background. There you go. Well, I'm glad you're here to verify that stuff. Punch cards are 60s, so it's before them. Wow. Okay. Maybe I should do my research before. Like, I'm not going to throw in any more anecdotes of things I haven't researched. I think that I should be more careful about that. Okay, so let's talk about debugging. And so there's a few things. We're going to look at what types of errors we can get in our software, because the different types of errors are going to be dealt with in different ways. And then we're going to talk about how to find these errors. I'm not necessarily going to talk about how to correct them, because I think correcting them is the same as the craft of programming itself, is saying, oh, I built this incorrectly, now I will rebuild it correctly. Whereas one of the biggest problems we get when our code is not working, like a program's not working the way we want it to, is just finding out which part of it we actually need to change. People are getting really detailed on exactly when in the 1940s this term was created. Okay, so what is a software bug? And we're going to interchangeably use the word errors and bugs in this case. I'm going to start calling them bugs in general, because that, funnily enough, even though it's a made-up word, and debugging is a made-up word, I would now consider them to be completely standard terms that we use in computer science and in the computing industry. Like, if you ask someone what a bug is who knows about programming and computing, they know what a bug is. It's not something that is only part of the community knows about. It's something that everyone kind of gets into. So we're going to look at defining this so that we understand it well. So in the beginning, the way that we think about it is every error in our code is a bug. Every error in our code has to do with what we wrote. So at some point we have written something in it, and then the program is not running as we intended, And there could be a few different reasons for that. So I'm going to talk about two bugs that are the common ones that we're going to see, especially at this level in COMP1511. One of them is syntax errors, and the other is logical errors. So a syntax error is an error in the language and our kind of use of the language. So remember I said before that C and the way that your computer is going to read C is highly specific. One letter out of place. If you have one letter out of place in what you write in a subject about a language, like say you're learning another language like Japanese or something like that. You have one letter out of place. Someone's still probably going to understand what you're saying, but they might say, oh, there's a little issue there, but don't worry. I get what you mean. It's all right. C will say, no, this entire program won't run. One letter out of place is enough for the entire program to just simply, DCC will throw its hands in the air like it just doesn't care, and it will say, this is a completely invalid program. You have like 1,000 lines of code and one letter out of place, and your compiler says, I will not read this, and I will not turn it into executable code. So that's where our syntax errors come from. Syntax being a word that means the little bits and pieces of a language. So with that specificity, I kind of knew I was going to say that word wrong as I started saying it. With that specificity, these little mistakes are going to be errors that are going to come up and cripple your code. So we're going to look at how we're going to detect and correct those errors. The best way, that we can grab syntax errors and correct them is to use our compiler. So when we're trying to figure out whether or not our computer can handle reading what we've written, the best thing we can do is test it, in a sense, by getting the computer to try reading it and having a look at the errors that come out of it. So we're going to look at what happens when we get errors from our compiler, from DCC, and we're going to look at how a simple process for going about those. So it's actually really, really simple, this one, but it's something that will make life a lot easier for you and sort of reduce the stress of what happens when you compile something and get a lot of errors. I'll show you that when we get to it, because we're actually going to do some live debugging. Logical errors are much more interesting and much more devious than syntax errors. Logical error can come from a program that is running. So I've run my compiler, and then the program is running. And when the program is running, it must be syntactically correct for my DCC compiler to have accepted it and translated it into a program that can run. But it might not still be doing what we intended it to do. For this example, this is like you writing something in a lab, for example, and then compiling it, it runs, running the auto tests and the auto test saying, you've only passed some of these tests. And you say, yeah, but I wrote all the code. I'm pretty sure this is going to work. And then auto test is saying, no, under these particular inputs, your program doesn't do what the specification said. Now, we're not always going to have auto tests, so sometimes we have to find out for ourselves whether something's working or not. We'll do that as well today. And then what we need to do is figure out what went wrong. And there's a few different things that can cause that, right? So sometimes we just read the question wrong. We're humans. We're not like computers. We don't read things perfectly exactly first go. We don't memorize everything perfectly exactly as we go along. So if we read the problem incorrectly, then in our testing we may find that we don't match the specification anymore that we were writing for. And we can say, oh, okay, I misunderstood that, which means I need to rewrite some of my code. Or we forget why we're writing the program in the first place. This is always the funniest one. It's like 3 weeks into a project and you've got all this code, you've built up all this amazing stuff, and you talk to your colleagues and you go, oh, look at all this towering edifice that I've created that can do all this stuff. And they say, wait, weren't we supposed to be doing something that solves this problem? Like, aren't you solving a different problem? And you just go, oh, I've done it again, haven't I? And this is the beauty of it, because what I'm teaching you is what I'm trying to inspire you with is like the joy of programming. And the joy of programming is just the creativity of this problem solving, the creativity of being able to create all of this wonderful code and stuff like that. But if we do that and we get so far off what we were trying to do in the first place, then yes, we are creating art. But when we're supposed to be engineering a solution to something and we create art instead, then we may have a problem. The ultimate goal is to create the art that solves the actual problem. But it's very easy when we get caught up in things to forget the problem. So we get into this situation where we forget the initial goal and then we solve the wrong problem. And so that's one thing that comes up. Another thing is we forget how the program might be used. So we test things that we think work for the program. I do this all the time. And you'll notice I do this because when you ask questions, sometimes I say, wow, I hadn't thought of that. And it's like, Mark, how come you hadn't thought of that? You've taught this so many times, and you wrote these programs, you know them. And one of the blind sides that we get, or like a blind spot, I think, that we have when we're programming, is because we know the back end of the program and how it's supposed to work. Sometimes we never test it for ideas that people have about how it might work or how they might want to use it. I've got I won't give it away. There's a slide later on, which is the slide before the break, which will show you a funny, just anecdotal example of that. There are actually engineers who work, and their entire engineers who work, and there are other engineers who don't work. Well, there's plenty of people who don't work. There's a position in the computing industry called a QA engineer, quality assurance engineer, and this person's just there to test. And so what they do is they kind of put together a skill set of second guessing all of the interesting things that people might do with a piece of software. And so they can come and look at our software and say, we can break this. And you say, please don't do that. And then, but in the back of your head you go, okay, please don't, but then again, please do. Because if you break it before I release it, then I'll be in a much better position because I'll have fixed all the problems. And so it's like the QA engineer's job to find out all the different ways that this can go wrong and help us with it. We as programmers, but I mean, some of you may end up QA engineers, if this testing thing becomes something that you really love. Regardless of whether we are specifically testers, anyone who builds code needs to be able to test it in at least a certain way, to be able to pass it on to other people and say, I'm pretty sure this mostly does what it needs to do. Okay, so how are we going to find these bugs? There's two things that we're going to use to do this. The first one is our compilers. So DCC is our compiler. Let's recall what it actually does. It's going to read all of our code, and if it finds our code to be correct C, it's going to translate it into something that then can be run on our computer. It's going to translate it into a program. So that reading and checking whether it's exactly correct for the translation is where it will catch syntactic bugs. So it will be reading our code line by line, and it will say, at this line, something doesn't work. And hopefully with a compiler that will tell us what's going on. And so I'm going to give you a really, really simple technique. It's actually going to not take me long to tell you how to do it. That's going to be one of the easiest ways to systematically knock out all of the syntactical bugs that are inside your program. And then logical bugs, there's a few ways we can get around them. Code reviews are pretty good for that. So if you, if in this week's tutorial you volunteer for a code review, you could bring in code from any of the labs previously. You could especially bring in code where you can say to everyone, okay, here's the lab from last week or the week before or something, and here's an exercise I couldn't finish, and I passed most of the auto tests, and I think most of my stuff is correct. What do other people think about this? And then they can actually talk to you about ways that they may have solved the problem, and then you could learn different ways to solve it and things like that. Pair programming is pretty good for that as well, because sometimes, you know, if you're the ideas person at the back and you're saying, oh, we need to do this and this and this, and the person in the front just sort of looks over their shoulder, if you are in person, which is unlikely because even the in-person tutes, you're not going to sit next to each other. That's breaking the social distancing rules. But anyway, if I was to metaphorically look over my shoulder and say, why are we doing this? And then the ideas person says, all right, that's not the question, is it? Okay, let's think about another way around this problem. Sometimes that really helps getting rid of those logical bugs. The other thing that we're going to do, and we're going to do this as if you're alone, because you need to be able to do this alone. It's not always going to be relying on other people to help solve problems. But we're going to learn how to test our own code. So we're going to learn how to verify which bits of the code are working and which aren't, and we're going to figure out how to narrow down where the problem is. Because generally, once we get to larger programs, like anything over sort of 100, 150 lines, you don't want to read it all to find out what's going wrong. You really want to narrow it down to, say, 5, 10 lines and go, okay, my problem's likely to be somewhere in here, or it's manifesting somewhere in here, and we're going to figure out exactly what the state of our program is in that area of code, and then we'll figure out what's going on. So, I have very little space on this slide so that I'm not covering up text. I'll just duck. I've just squished my camera a little bit there. So, as I said before, simplest thing that we can do is run DCC on our code and just see what happens. We're going to get errors and warnings. I would initially not worry about the distinction between them. There is a distinction between an error and a warning. That's when you print out with DCC, warnings will default, they'll be in pink, and errors will be in red. The technical difference between them is that a warning tells you that something might be wrong, but the code is syntactically correct and it will still be able to compile it. An error says the code is not syntactically correct, I cannot compile it. And the code will not be compiled. So there won't be a program at the end if you have any errors. If you have warnings but no errors, there will be a program, and good luck to you if you run it. Personally, if I have warnings and I've created a program, it's rare that I will run it. Because if I've got warnings, then I know something's going to go wrong. So it's not worth it to me. I usually fix the warnings before going on. So the golden rule that I have here for compiler errors is always start with the first error. I'm just going to say compiler errors here, and I'm going to put warnings and errors together. So anything your compiler tells you to do, read the first thing that it says is a problem and fix it. So what I'm saying here is ignore everything after the first issue, because there's going to be lots of them in most cases, because if you have any, you've got a lot. It's not always the case, but a lot of the time, if you have any, you've got a lot, because that first error causes the translator to think it's reading something different from what we intended. And then there'll be all these other errors that happen afterwards. And maybe fixing that first one will remove all these other errors. Maybe. It's not always the case, but it can help, right? So I always start with the first error. I only read the first error. I only fix the first error. And then I compile again afterwards and look at what errors there are afterwards. That is the most simple thing that is going to make your debugging more efficient. So we only look at the first issue that our compiler finds, and we fix that. The other thing to think about is that the error that you're seeing... as Tom's saying, we're going to do this when we demo, is trying to find where your last DCC command was is actually super annoying, because they all look the same, and there'll be just one line where you had a command prompt, but I'll show that when we actually do it, because we're going to do a bit of this live. The error that you get from your compiler may not be the error itself. It may be the consequence of the error. So it may be because when you think about the compiler translating your code, what it's going to do is it's going to find a place where the translation stops working. So if you've accidentally written something strange that has misled the code, it won't know that there's a problem until something doesn't match up. So you may be seeing the consequence of the code, a consequence of the error rather than the error itself. You will always at least get a line and a character that the error is on. The character is not as important, because usually we have one operation per line. Again, reasons why we have one operation per line. If we know the line number, we know the thing that's triggering the error, and we know that somewhere above it something caused this line to fail. And so if we know that, we can kind of trace back and find out the cause. when we're digging further into solving these, we've got the line number, and sometimes that's all we need. Sometimes knowing the line number and reading that line of code is enough for us to say, oh, I see exactly what's going on. The other thing is to actually read the error message and interpret it. This can be quite difficult because error messages can be really kind of arcane and strange. The error message may be assuming that you're trying to do something with your code that you don't even know how to do yet. Because if we have a typo in our code, we don't know if there's a magical symbol for some other thing in C that we've typed in, and our program thinks that we're intending to do something. And the compiler's not a human. It doesn't have that kind of second level of reasoning. All it says is this is wrong, and DCC in particular, more than other compilers, is going to have a stab at what you were trying to do, because DCC was written by one of the CSE academics, Andrew Taylor, and he knows, because he's been teaching. He actually taught me when I was a student, which is pretty cool. He knows a lot of the errors that students make, and so he puts little bits of text in there saying, I think that you might have been trying to do this. This is a common mistake, and this is how you get around it. So reading the error message might help you figure out what it is. If not, at least you know where it is. So some of the things that the compiler is going to tell you is like, I was expecting something here and I didn't get it, or this syntax is not what I expected in this position. So sometimes it's easy because if we're calling a function, we expect the open brackets to have a closed brackets. If we have a line of an operation, we expect to have a semicolon at the end. So knowing that that structure is strict means that we know that the compiler will catch things in specific circumstances. But it's not always the case. I have an example. I've set up a perfect example. Well, it's a perfect example. I set up an example that shows some things like that. So let's go on break. It's going to be a bit of an early break because I didn't want to break up the example that's going to happen afterwards. But we're going to put that into practice in a second. So this is the example that I was talking about QA engineers. So this is a tweet from a few years back. And I don't think this was the first time this has been tweeted or anything. So it's like, a QA engineer walks into a bar, orders a beer, orders 0 beers, orders 9999999 beers. This is what we do when we test, right? We're going to test things in many different ways. Orders a lizard. Right? It's worth testing to see if you can deal with invalid input. Orders -1 beers, orders spam the keyboard, right? And the QA engineer at this point says, yeah, you can deal with anything. And then the first real customer walks in and asks where the bathroom is. The bar bursts into flames, killing everyone. The number of times this has happened is, not bursting into flames and killing everyone, but the metaphor of what's going on here, the number of times this has happened is nearly to the point where that's why this is funny. Because this is what the software industry is like. We have historically a very poor track record of guessing in advance what our users are going to do. The software industry has had to, over the course of the last kind of, I would say 30 years, work again and again and again on engineering principles that people in other engineering disciplines had really kind of nailed down a long time ago and had good ideas about these things, which was actually getting into the mind of your user and trying to work for what they might do. So it's really, really interesting that this in 2018 is still a funny tweet. But we're getting there bit by bit. There are actually, and this is actually an interesting thing because sometimes I get questions from people saying, I'm really bad at programming. Should I not do computing? And it's like, that like programmers are only about, I think it's like 30-40% of the computing industry. We actually need these QA engineers. We need these people to understand people better than they understand computers. Because if we're going to make stuff for people, then we need to understand people, right? And we actually have a lot of roles in development teams for people who whose entire job is the psychology of human beings and what they might do with things, and how we can use what we know about the psychology of human beings to make our programs actually serve them better. And so this is that idea, right? It's like, of course someone would ask a question like that, but we didn't think about it because our specification and our goals for the program never included that. And we didn't think that just because we have goals for the program and just because we have a real tight specification doesn't mean someone else isn't going to see this program and act naturally towards it. And so that's like, yeah, super interesting. Anyway, we are at about 11:55 now. We will come back at exactly midday and we will continue and we'll do an example of actual debugging and stuff like that. Okay, see you in a moment. All right, we're back. Thank you for the questions, Kevin. I was like, usually in the break, someone will ask a question and be like, "Oh yeah, I'll just type a little answer there." It's not often that it's like, "Oh, this movie or this movie." Also, I should point out that whenever I talk about anything that's not specifically related to programming computers and things like that, I am not the authority on this, and everything that I say in those regards is entirely opinion-based. I say this because at one point when I was teaching, 2 students tried to use me as the arbiter for whether or not they should eat sushi. And it was a really, really weird conversation. So one of the students was saying, "Would you eat raw chicken?" And so they asked me, "Would you eat raw chicken?" I'm just like, "Well, not necessarily. I don't think that's that healthy." And he was like, "See, you shouldn't eat sushi." And I was like, "I'm not sure. I did not say you shouldn't eat sushi. I like sushi. I don't know what's going on here." So it was just like a really funny moment where people were trying to use me to decide whether something was actually happening or not, or something was right or not. And it's like, I'm not a nutritionist. You should not be using me as an authority figure for everything. And Eric's like the arbiter from Halo. No, I don't go invisible and have like a laser sword to cut things up and stuff like that. Although I wish that I did. The arbiter would be, like, in terms of sci-fi characters to be, the arbiter's story arc is pretty cool. That would be a cool thing to be. Anyway, let us continue. So, we are going to look at a program and we're going to fix some bugs in that program. I'm not covering up that many letters, half a letter there, so that's okay. So, here is another meme that is a very, very common meme. I've made the mistake of talking about food in a lecture that goes through lunchtime. At least this is streamed. You could technically be eating now while I'm lecturing, and you won't be like bringing food into a lecture theater and encouraging like rats at UNSW or something like that. So you could if you want to. But this here is very funny, and we laugh about it because it happens. We've got bugs. We get rid of the bugs, and all that does is give our compiler access to more sections of the code where it can find more of the problems that we have in our code. So this can happen. I think the example I've set up today is simple enough that it's not necessarily going to happen. Yes, and Trent said, if you don't laugh, you cry. This is the laugh cry meme here, which is why Grumpy Cat is here. I don't know how many people know of Grumpy Cat, because Grumpy Cat died a few years ago, so I think the memes of Grumpy Cat have kind of faded out by now. But, you know, people still know about it a little bit. Okay, so, oh, no. Sorry. I was supposed to jump. I just went to the spoiler slide instead of going to the code itself. So hopefully no one read what was in that spoiler slide. I mean, we'll see. So the code that I'm looking at here is code that's in the lecture section of the course website. So I've put this up in advance so that you can see it. The nice thing about this is old code. I wrote this code a year ago, 2 years ago. I don't know. I edited it at some point. But the idea is that I can't remember all of the errors that are in this, but I know that it's set up in a particular way to show a couple of different things. So we'll have a look. I've prepared this in advance, lecture 9 directory, and I've got it here. Yeah. So we'll have a look at this code, and I will put the pantomime rules in effect. Where I've told you about this before, right? We're talking about the kids' pantomime show, where some of you are going to see the issue coming up. Some of you are going to see exactly where I've done something wrong. I encourage you can yell out, "He's behind you," if you want to, but don't necessarily say what the error is, because we're going to go through the process of finding it. And if we already know where it is, it's less useful to think about the process. So you can yell out, "He's behind you." You already started. Yes. There you go. He's behind you. Yeah. So, so what we'll do is we'll go through this And I want to step through the process. So even though you can, some of you, Guru-chan already has said, I've seen one of the errors. Even though we can see the errors, what we want to do is we want to learn how to find them if we couldn't see them. So this is what the deal is with this pantomime thing. Yeah, Dora the Explorer stuff going on. Okay, so instead of saying I could just look at this code and use my giant brain to find it, what I want to do is prepare you for situations in which your giant brain is not big enough. Because we're all going to find that at some point, that we believe in our giant brain and we trust in our giant brain, but the giant code is bigger than our giant brain. And so if we can't find it, what do we do? And so that's the situation I want to prepare you for. I don't need to prepare you for situations where you can just look at the code and fix it. What I'm preparing you for is situations where you look at the code and you say, that is 100% correct code. And then you compile it and your compiler says, no, it is not. And then you can't argue with the compiler because it is right. Like, I don't know. There's potentially a possible situation somewhere where the compiler isn't correct. But the chances of us finding that are so low that I think acting on the assumption that the compiler is correct and I've made a mistake is much safer. So instead of looking too deeply at this code, I am going to just compile it. So I'm going to run this code into DCC. So debug this. I guess I should at least say what this code is. So this code is intended to loop and draw a square of asterisks size based on the user input. So once we actually get to running this thing is supposed to take in a number from our user and draw a square of asterisks that is sized based on what the user asked. And then when it's done doing that, it will ask us again what size we want to draw, and then we draw it. Not super important because it's not running just yet. Well, I'm assuming it's not running. If it is running, then that's very bad because I put the wrong version of the code up. But, okay, so I'm just going to call it debug as the program we're trying to create. Okay, so as expected, because we knew that this was a debugging exercise, there's stuff to debug. Okay, so there's all these errors here. As I said, I'm going to ignore them. I'm going to scroll up, all the way up, and ignore all of these errors because I don't know if any of those errors are a consequence of the initial things. So the first thing I see here is a warning. Using the result of an assignment as a condition without parentheses. Place parentheses around the assignment to silence this warning. I'm not sure if I want to do that. Or use double equals to turn this assignment into an equality comparison. Ugh. When checking for equality in the condition on line 17 of debugthis.c, try using double equal sign instead of a single equal sign. Okay, this is good. And I did see Guru-chan's message before they deleted it there. Yes, this was the one that you spotted. So note that I'm not reading any further than this because there's an error here and some other stuff. Don't care. Not worried about that yet, because what if this first issue was the thing that caused other issues to happen? So let's fix this one first, and then I'm just going to let that go. So here I said exit equals 0, and while exit equals 0, I want to do some stuff. And so obviously in my while loop here, I was intending on checking that, and something in here is probably going to change exit. Yeah, so I have other ways to change exit. So what I'm going to do is say that this should have been a check. It shouldn't have been set exit to 0, because then that while loop would probably run forever. Instead, what I was going to do was check if somewhere in this we'd flicked it to 0, in which case the while loop wasn't going to run anymore. So I set this to the double equals that it should be. I'm going to save this, and then I'm going to come in and recompile. And as Tom and the others were talking about here, let's see, if I just recompile, I've got all these errors again, and I scroll up, and it's really hard for me to see where the errors ended. And if I keep going, I'm probably going to end up at a previous compile line. So it's really hard for me to find. And so just to make things easier for ourselves, we can clear this, which says, okay, I don't want to know about anything that happened previously. And then I'm going to run my compile command. Oh wait, even clear is going to... Yeah, no, clear after we run it is going to be able to see more than one command. So clear is not that great. The other option people are saying is press enter lots of times. So now we have this big block of these command prompts here, So when I compile, it'll be really easy for me to see where my most recent compile command is, and I won't accidentally scroll past that line and read into errors that are errors from a previous version of our code. So, any questions we had there? Tom saying you would occasionally argue with the compiler. Yeah, Osama is a very good question, because compilers are written by humans. Compilers do occasionally have errors in them. It's very hard to deal with an error in the compiler. Usually what that means is you have to find a way to contact whoever wrote the compiler and talk to them about the errors in it. Luckily for us with DCC, the compiler is like what we call in-house. Andrew Taylor wrote it here. He's only one email away for myself and Tom and other people. So you could do that. Oh, All Nighter is saying use the reset command. So the reset command, so clear just clears the current screen, whereas the reset command, I think, will say we get rid of all the history of what we had before. And now if I run my compile command and I scroll up, I'll hit the top here, and so I'll only have my current compile command. So reset's probably better than clear in this case when you're doing your debugging. I guess the only downside is if you actually wanted to go back and read previous error messages, but I would suggest that you don't really read error messages from code that's before you made changes. Like previous code's not necessary. Okay, so let's look at another syntax error that's coming up here. And again, I will only look at the first error. So I've got this one here, and I won't necessarily look at this other error and other stuff yet. I'm just going to look at this. Error, expected parameter declarator. Printf, thank you for using GoodDraw, have a nice day. Line 47. Line 47 here. Just having a quick look at that. Code doesn't look too weird to me, so there's got to be something else going on. If you're trying to call a function on line 47, be sure that you're calling it inside of curly braces within a function. Also check that the function's header, the line including introducing the function's name, doesn't end in a semicolon. Okay. Alternatively, if you're trying to declare a function or a prototype, be sure that each argument for the function is formatted as a data type and followed by a variable name. Hard to see what's going on here, but we've got a few clues. If you're trying to call a function, make sure that it's inside curly braces. If you're trying to declare a function, make sure that it's correct. Now, we are certainly not trying to declare a function here. This is printf. Printf we know exists. We can check something like this. Maybe this is the kind of error that we would get sometimes if we haven't included standard input output and we use printf, but we have here, so that's okay. We think that's fine. So we were trying to call a function. If you're trying to call a function, be sure that you're calling it inside of curly braces within a function. Okay, close curly braces is here. So we're inside the function. I'm waiting now for anyone to yell out, "He's behind you!" See if you can see it. So, one thing that we might want to do here is look at whether we are actually inside curly braces. So this is a very common... Yeah, Kat's seen it. Okay. And Ethan's seen it as well. So if I'm... One of the nice things about a lot of editors is whenever you click or have your cursor near a bracket, it will try to highlight the other end of the bracket. So we've got this here, and these are nice, right? So we can see that our open and closing brackets are nice, and we see that they're lined up nicely as well. This is another thing about this is going to be easy to spot because of how we've styled our code. And I've got my while loop that opens there, and wait, the while loop opens here and ends here. And look at this. We have two closing brackets that are vertically aligned with each other. This makes no sense to me as a programmer. I would never have two closing brackets aligned. Because if they were aligned, then that means something else had to open a bracket somewhere for this one to close. So this one looks right to me. There's a while loop, and inside there's another while loop. Oh, wait up, is that correct? Maybe it isn't. Maybe this is the extra one. And if we look at at the the outer end of the detail here, we've got this bracket that opens our main, and it closes here. So Shrey said that last night, working on other code, you had exactly this error, and this error comes up a lot. So just one mistake in the bracketing has now made our main function end here, which means our printf is outside of the main function, which is why this is saying, be sure that you're calling it inside of the curly braces within a function. So DCC can see that. It can see that this printf is actually on its own. It's not inside the main, because we accidentally closed our while loop too early here. So let's try that. I think this will be correct because it's the while loop here goes to here, and if I click on this one, scroll back up to there, our main now is covering everything in our program. So let's see if that works. Did I save that? Control S just in case. I will reset. So I'm using my up and down arrow keys to just go through the history of the commands that I used. We will compile this. It's taking longer than I expected. Oh, good. So obviously our program is complete now and it's 100% working, right? There's no problems. This can't possibly be wrong. This can't possibly be an example in a debugging exercise that's set up specifically to not just have syntax errors, right? Oh, Ethan, if you recall, the -O tells us what the name of the program is that we're creating. So if I do ls, this -O is the name of the program that can run after it's read this code. So DCC will always have the file name and then the output file. Okay, let me go back to my slides for a second. So, what errors did we find? What did we discover? So here are the spoilers. So we had the single if statement and the extra bracket, which had a lot of issues and a slightly odd error message. So I just wanted to show that one so that you could see what was going on there. Those are obviously not all of the possible errors that you could get in your code. Okay, next thing we're going to do is we're going to think about testing. Test parts of our code to make sure it's working. Simple things, we're going to run the code. We're going to run the code with different inputs to see different situations of what happens. The auto tests that we've given you for a lot of the things in COMP1511 are us doing testing. So it's nearly like one of the tutors or lecturers or subject admins in the past of the subject, so we build up our bank of questions over many years, has written a program and said, how would I normally have tested this? What are the kinds of inputs I would have put in to test this? And that's what your auto tests are. None of your auto tests are computer generated or anything like that. It's actually just us saying, how would we test this? What are the types of inputs that I think are important? You know, so if we have a lab question which has arrays, we'll have like, okay, important bit happens at the beginning, ooh, important bit happens at the end or in the middle, or we'll have like, ooh, what happens if something's off the end of the array and stuff, you know, those are the kinds of things we test. When you're learning about how to build code, you're going to learn about like, what kind of tests do you want to do? So we try inputs that we expect to see and try some inputs that aren't expected and see what happens. But then we need to know, how do we know whether our tests are working or not? Maybe we need to do things with our program that are outside of our goals and our specification. Maybe we need to get our program to tell us more about what it's doing. And so what I'm going to do is, as we do this test and we build up to diagnose what our errors are in our code, we're not just going to fix them straight away. I'm going to show you ways to diagnose what's happening in the code. So look away for a second and make sure. Yep, okay. I was like, is the next slide the spoiler slide, or do I have more specifics on the next slide? I was going to get ready to switch back really quickly if I accidentally spoiled it again, because I never remember exactly how many slides I have. I remember what concepts I'm teaching, but yeah. Okay, so a couple of things that we're going to use every time we're testing code is, we can write stuff into our program. We can write stuff differently in our program to give us back information. So when something runs, it doesn't just crash. It tells you what it was trying to do at that point in time. So at the point where we know our program isn't running correctly, then we can start adding things to our code to find out what we're doing. And we can also say, test one thing at a time and test with a specific idea of what we want to find out. So we can say, I know that this particular loop in the program isn't ending correctly. So I'm going to test for how that loop ends. So I'll put some information in there that tells me when that loop is trying to keep going or when it's trying to end. I'm going to put the kinds of inputs in that will cause it to end and then not cause it to end and stuff. And then what you kind of do is you've got like this needle in the haystack thing. You've got thousands of lines of code. One line is the problem. What you can do is basically separate your code into different parts and find out which small parts are the problem and then go in detail. What I was saying before about how splitting your code up into functions means that each function does one purpose, this makes it even easier because you can say, I'm going to test only this function. And I've even got to the point where we've had situations where we're pretty sure that one function is the problem. And what we do is we actually copy paste that function's code into a fresh file with a blank main. And we say, okay, now we will test this function on its own without anything else getting in its way. And sometimes when we isolate it like that, we know exactly what's going wrong. There's a whole field of testing that people call unit testing, where we break down our program into individual units of capability and test them without anything else interfering. And sometimes that's a really, really good way to make sure all of your little components work individually, and then when you stick them together, you find out if the whole thing works, but your kind of judgment won't be clouded by possible errors in the individual components. So, lots of different ways we can test. But I'm going to show you. I'm pretty sure the next slide is going to be a spoiler slide. So let's go back to the program, which we have now, because this has compiled. We know that there are no syntax errors in this program. Therefore, the program must be amazing and must be ready to submit. So I'm ready to release this to the world. Please give me my millions of dollars of venture capital seed funding for my new app called Debug. So let's run this. You can tell, right? You can tell. I hope people can tell. If I'm building something up this much, it must be because it's about to fall over. Okay, so size of grid I would like to make. Let's go easy on it. Let's test just a size grid that we're going to be able to read, we're going to be able to see easily. So it's going forever. It's not stopping. I'm scrolling up and down, but nothing changes. Okay, so I appear to be in an infinite loop. So if I'm in an infinite loop, let me press Control C. Control C is going to end this program here. We're really lucky because we're using DCC, and DCC is actually telling us where it stopped. As opposed to, like, I don't know if anyone's used any of the other compilers and you've tried them. When you press Control C, it just ends. And it's like, okay, that's it. It doesn't give you this, and it doesn't give you this either. That's some stuff that Andrew Taylor wrote into this to get it working really nicely like this. So, okay, we know that somewhere in this double while loop in here, this is where we stopped. We don't know whether this is just exactly when I pressed Control C. Because if we look at this, it was drawing stars, and there could have been a chance maybe that I pressed Control C anywhere inside this loop. But we know it's inside the bigger loop because it stopped outside of that. So we know that there might be a problem there. So I know that there's probably a lot of he's behind you there. And your chance, like, it's right in front of you. Okay, so there's definitely some stuff here that's going wrong. I don't want to just look at it and say what's wrong. Because imagine if this while loop is, don't ever do this, but imagine if this while loop is like 300 lines of code. Don't ever write a while loop that's 300 lines of code. There's always an issue if you try to put too much in a single loop like that. But there are cases where it happens. Imagine if it's that big. You can't just look at it and see it, right? We want to have a better way of doing this. So I'm gonna use a technique here which will give us more information about what's going on. So what I'm going to do is let my program tell me where it is every time. So I'm going to put printfs in my code, and note that I'm going outside of the spec here. The spec definitely does not ask me to say random things in between these stars. It's supposed to just print out the grid of stars. So what I'm doing is I'm making this temporarily not meet the specification, but do that so that I can see what's going on. So I'm gonna say something along the lines of starting while loop, y is something. And so this way, I will get some information about what's going on. And the y, oh, the y is y, right? So the number I'm going to print out is the y. And then in here, I'm also going to do something like that. I'm going to say starting x loop, x is something. So what I'm going to get out of this when I run it now, I mean, obviously I'm just going to get even more text in this infinite loop because I haven't fixed the infinite loop. I know some of you can see where this infinite loop is, but that's not what I'm worried about right now. What I'm worried about is finding out what's going on. So this will tell me how many times the while loop is running. This will tell me how many times the x loop is running. So if I press Control-C at any point, I can go back through my output. And instead of trying to make sense of this, which is impossible, the only sense I can make of this is that things are out of control. Whereas the sense I can make of this is I will be able to start seeing what the looping variables are doing. The other thing, actually no, we'll sort that out later when we go to actually edit the code to correct it. But for the moment, let's see what's happening. Yeah, I've saved it. Always wanting to check that I've actually saved my code before I compile it, because that's one of the most annoying things. Is you compile code that's the old version, and then you run it and the old errors are still in it. Okay, so we know that this is going to go forever, but at least this time it's going to give us some information. So I'm going to hit Control-C pretty early here. Okay, so I hit Control-C because I saw that it was looping forever. And let's have a look at what's going on. So we have these sequences of the while loops, and each time the while loop runs, the x loop runs a certain number of times. And we start to see the issue. It's pretty clear what's going on here. That every time we're looping through this, y is equal to 0. Someone said they just ordered sushi. Yeah. And everyone's saying he's not just behind me, he's right in front of me. Kat was wondering why the police hadn't passed by in the lecture. I just live on a road that, like, yeah. I can't remember, the police station is just that way a little bit, and so, like, there's an entire series of suburbs in that direction that they're always going back and forth. Obviously, they're looking for me, but they haven't found me yet. My pirate stream is still broadcasting. Okay, so the issue that we're getting here, the issue that all those police still can't find, is that our y isn't changing. So let's look at our incrementer here. At the end of the while loop, we expect our incrementer to usually be at the end of the while loop, and we see this. And we go, what is that, and why is it there? X is equal to y plus 1. That makes no sense to me. This is going to be y is equal to y plus 1. The other thing is, maybe I want to keep track of y, and I'm like, oh, where are my loop variables? And they're up here. And I'm not sure I want my loop variables up there, so I'm going to move these to somewhere where I can keep track of them. Which is going to be, and this is going to be a rule that you can use a lot of the time, is create your variables as late as possible before they're going to be used. There is a school of thought, which I was using when I originally created this, that sometimes it's nice to see all your variables before you start doing stuff. For some of them it is, and for some of them it's less so. When I'm using looping variables, sometimes I want them to exist only where they're needed. So the y equals 0 here, and then this, here I actually want my x equals 0 inside the loop. Because here I was doing this other thing where the x was outside, and so what I was doing was setting x back to 0 each time. But if I only create it inside the loop, I might actually be in a better position where I won't have to do this resetting of x that I've got here. Okay, I've changed more code than I should have for that error, but let's just look at that error now, and I'm going to leave these statements in there now because I still want some diagnostics, right? I still want to see whether this is working or not. So let us compile this again. Don't worry about these warnings if you see them, the gedit warnings. These have come up heaps, and they're actually only based on the autocomplete code in gedit, where it's like looking for words that were in the code previously to see whether those are the words you want to type in again. I think this happens when you delete words and it can't find them, but don't worry about it. These warnings will not affect your code or even how gedit runs. Error, use of undeclared identifier x. So I'm setting x equals 0 somewhere. 43, 43. Okay, that's resetting the variables of x and y for subsequent loops, but now I don't need to reset them because I'm setting them specifically just before I use them. So I don't think I need either of those. I'm going to get rid of that. Yep. Okay, I may not even need that one, but I don't really know what that does right now, so I'm not going to touch it. But I know that the x's and y's, because I moved them to a more convenient place for variables, I know they're always going to be set to 0 just before they're used, which is the safest way to use them. And now I can read them sort of locally to where they're used. Alright, so let's save that, compile that, and hopefully we'll compile correctly this time. Okay, now let's see if we've gotten rid of our infinite loop problem. We'll do size 4 again. Okay. Y is 0, Y is 1, Y is 2, Y is 3, and it ends. Great. So now I know that my infinite loop is not a problem, and I can enter the size of the grid I could like to make. So we're going to make one of size 8. Size 2. Size negative 150. Hey, it can kind of deal with that. I mean, it's just rejecting the input, which is fine. Size, hello. It has taken my hello to mean that I said I don't want to deal with you. It's taken my hello as a goodbye. That's okay. I'm okay with that, because if I'm going to give it input that is so far outside of what it's supposed to have, maybe it's okay if it just doesn't use it. Okay, so I think I don't need this looping diagnostic stuff anymore. What I'm going to do for the moment is comment that out. I'm not going to get rid of it just yet. If I was going to publish this, or if I was going to submit this as my final version in an assignment, then I don't want these. You know? Because someone's going to read these as if they are an English language explanation of what's coming next, like this one. And if we have these in the way, they're just going to, like, it's like spam. You know, they're going to make us read things that we shouldn't read. But for the moment, because I don't think I've finished testing, I don't know if I've gotten rid of all the logical errors, I'm going to leave them in case I need them to come back. What are we... oh, we're talking about the police looking for me for the code that I'm writing. Okay, I don't know if anyone else is still yelling out he's behind you, because there might be something else going on here, but let's see. I'm going to compile this again and run it. And let's have a look. So I'll do size 4. David is yelling. David is yelling. And what was Kat was saying? Oh, yep. Okay, well, let's not spoil it for everyone yet, but we'll see it. I think everyone's noticed. Okay. Size 4, I've got 4 rows, which is good. It looks pretty squarish. I'm just trolling you now. You can see the problem, right? There are 5 stars in each row. So this is really kind of appearing to be correct now. This is like getting so close that we think, oh, we could nearly use this, but it is still incorrect. So there's 5 stars in each row. And so now we need to go and we look in and we say, if there's 5 stars in each row, then it's something about the row loop here. And we say, okay, what are the things that can make this run more times than it should? And here is the point where there's no more tricks that I can teach you, because you've narrowed this down to something so small that either there's something here that this is printing more than 1, or we have a look at this and we look at what's going on with our consistency in our loops here. This is not consistent. This looks okay, it's consistent with this, and so it's probably just this. if we do less than or equal to, we were creating an extra one. So sometimes this is us analyzing this output and saying, where in the code is this output happening? So a lot of this is going to be, how well have you structured your code? Do you have a comment that tells you what's going on at each point? You don't have to have comments through all of your code. So sometimes you only have one comment outside the big while loop, that kind of thing. Or if you'd done this the way we did similar things in other lecture exercises, this would have been inside its own function. And if this is inside its own function, then it's really easy to say which function is printing the rows, and we only look at that. And so that's why I say sometimes splitting stuff into functions is really useful. I could find this piece of code because I know enough about this program now, after having debugged it for a while, this is where it is. But if it was in a function, it'd be even easier. Okay, having corrected that, we'll save that. I think we still need to type 0 to exit because the old version was still running. Compile that, run it. Size 4, 4 by 4. Size 7, I think that's correct. Size 2, size 1 even. Size 15. Alright, we're good now. Size 0 to exit. Alright, so I could also have tested other things, but you saw before I tested things like words, I tested negative numbers and stuff, and I had done enough here to make sure that it worked, because I did have a scanf in there. Oh, actually, let me try asking for the bathroom. You're all gonna like, this is gonna be really funny. I think from here on, everyone's just gonna type in bathroom for things. Oh no, we're not out of the woods yet. We were mostly there, because of something that I'd done here, where every subsequent loop, and see, this is the thing, we definitely tested a word before, right? We tested a word, we tested hello, and that worked, and we thought, oh cool, we can deal with words. The only reason we could deal with words is because we set the grid size to 0 after each loop. But setting it after each loop does not protect us the very first time. If this scanf doesn't work, and then we test grid size, if it didn't have a value, then we have nothing. So what I'm going to do is I'm going to get rid of this whole section here that I had this idea that I was resetting variables at the end of the loop. And instead of doing that, I'm going to try to do this up here, where I have a grid size that I am going to scan in like that. And again, I'm going to do the same thing, where I'm going to try to use my variables, declare my variables as late as possible before I need them. And I'm also going to initialize this so that if something goes wrong, it deals with it. So I'm going to say the grid size is 0. 0 is what I consider a safe value for this program. Not for any other program, but just for this program, because I know that if the grid size is 0, nothing will get printed out. So if I was to do grid size is 5, any mistake in scanf would allow the grid size to then print out a grid of 5 by 5. So what I want is that if there's a mistake in the input, that no grid is created. So that makes sense to me there. But this program will still function. So if grid size is equal to 0, exit is equal to 1. So that's good. If I don't get proper input, the program's going to end. So I remember, like in the second week maybe, where I was looking at how do I deal with incorrect input? What am I going to do with it? This is one of those examples where it's like, incorrect input, I'm throwing it away. There is no way I can generate useful input from that. So save that. Reset here. Compile that again and run it, and we'll see if the bathroom destroys it again. Okay. Nice. Okay, at least now we're returning 0, as opposed to exploding in different ways. This is by no means a full set of tests for a program like this, but what hopefully I've shown you here today is getting us to the point where we have, oh sorry, there was another slide there about some of the things about checking what it's supposed to do, checking a range of inputs, and then putting those printf statements in. So this is a slide that just kind of covers what we've already done. So let's think about what we did. We tried 0, we tried negative numbers, we tried random things. We were outputting the x and y values to see what they were, so we could see whether they were working or not. That told us why the infinite loop was happening. Because there were kind of two options for the infinite loop. It could have been the x loop or the y loop, but a bit of diagnosis told us that. I mean, yes, some of you did look at the code and see that there was an issue, but we want to equip you with the capability of dealing with this when you can't see it. So through this kind of testing, we were able, every time that we did our testing with our logical errors, we were able to kind of isolate parts of our code that were things that we knew were having problems, and those are the things that we then were able to work on and able to make changes so that our program ends up running. Okay, so someone Thomas is like, time for a bathroom break? No, we've had our bathroom break. And I used my entire bathroom break to talk about Aliens films. So I didn't actually go to the bathroom, which I normally would do in the break. But anyway, characters. So this is us kind of like, okay, that's the end of talking about debugging. We're starting a new chapter here. This is like big enough that I needed a bit of this lecture and the next lecture to talk about them. So we're not necessarily going to demo these today, but I do want to talk about them and get us a bit of grounding of how they work and a bit of information about stuff that we can do with them before Friday when we're going to continue these. So up until this point, we've been learning everything we've been learning about C with only numbers. Only ints and doubles, and even to the point where nearly all of our examples have only used ints, because the difference between the ints and doubles haven't been super important. But what we've been learning about is more not the variables themselves, but how to use them in different structures and things, which I think is the important bit. But now that we've got our handle on being able to use variables, and especially being able to use arrays, it's time to think about using more than just letters, more than just numbers, and introducing letters. So characters are letters like, for example, ABC, etc. But what it boils down to is that characters are actually, I mean, if we think about this in a really, really old school perspective, the characters are all of the keys on the keyboard. I mean, we have some keys on the keyboard that aren't necessarily characters, because they've been added to the keyboard subsequent to this idea of characters on the keyboard. So your Apple or your Windows button are not necessarily these. Even stuff like Control and Alt and stuff are not necessarily these. But most of the keys that you have in your keyboard are characters. So the numbers are characters because they're keys on the keyboard. Even things like space and enter are characters. I don't think the function keys and escape are necessarily characters, but each of them can be represented. And the funny thing about this is they're actually represented as 8-bit integers. So this char variable, the character variable, is an 8-bit variable. So this is the first time we've seen a variable this small. So it's right down at the very smallest size that we can address in our memory, which is a byte, 8 bits. And they're actually stored as a number. So if you want to boil down and see the very kind of under the hood details about this, these characters are encoded as numbers using this system called ASCII, which is, back in the day, I had to look this up, by the way, I don't bother memorizing stuff like this, American Standard Code for Information Interchange. And I was like, oh really, is that what I'd actually forgotten that. You know, I teach this every term and I'd forgotten that it was information interchange. Not super important. In fact, we will barely ever be using the ASCII table or the fact, well, we'll be using the fact that characters are numbers, but we won't be too worried about the actual value of them. We're going to do a little bit that, especially in the week 7 tutorial and lab, about how to use characters and how to kind of treat them a little bit like numbers, to do a little bit of maths on them and stuff like that. But in general, we're going to remember that they are numbers, but also use them pretty much as if they're letters. And the funny thing about it is, because they are 8-bit integers, our integers and our characters will now be in a certain regard interchangeable. So we will actually be able to store characters in integer variables, which is actually what we're going to do a lot of the time because of different reasons. I'll show you those reasons as we go along. So ASCII, as it stands, is values between 0 and 127. So 8 bits actually gives us 256 possible numbers. ASCII in its standard specification only uses 0 to 127. Let me show you. I'm just going to Google it. I love how it tried to autocomplete to ASCII art. But which one of these is going to be easy to read? That one's got colors. The font is tiny though. Okay, font is tiny, so not sure how well you're going to be able to see it. But here we have a list of the decimal and hexadecimal and even binary, octal, base 8 numbering system, of each of the characters that we can use. So you can see here are our numbers. Important to note, the number 0 is not represented by the number 0. Null is actually represented by the number 0. This is not always the same null that we have, by the way, so don't always assume null is 0. If you want to check if something is null, then check against the hash defined null, not as 0. But anyway, we have the numbers here, we have a bunch of punctuation here, we have some capital letters here, we've got a bunch of lowercase letters here, and you can see it goes from 0 to 127. This is the standard ASCII. Not super important, and please don't get into the trap of trying to memorize this thing. This is not what this is about. We don't need to memorize this. We can always find these values by just asking our computer to deal with them. So for example, if I said put capital A into an integer, then print it out as if it's an integer, it will do 65. And so that's nice. We don't actually have to memorize it. But in case you ever want to look at it, these ASCII tables are available online, and it's a standard that everything uses. All our keyboards, well, most of our keyboards will use it, so it should be reasonably easy to use the correlation between these things without knowing the numbers. So all those things are in there. Oh, I didn't actually show it, but even the space in the new line, like the enter key, are actually characters. They have their own ASCII codes and stuff like that. What are we saying? Oh, that's right. No, people are talking about different things. That's fine. Yeah, so I was saying not necessary to memorize, but we can treat them like numbers, which is good. So some code for us using characters, and usually there's a really, really funny thing that I've done here. Is I've said, here's this new variable type, and I'm not even using it. So you can see here, I actually used an integer for a character. This is because a lot of the time when we're working with individual characters, we will tend to put them in integers because there are some things that we can do with them that are useful as integers. So this character here, we are now using single quotes for characters. So double quotes we've been using in printf and scanf. When we have only one letter at a time, we will use the single quotes. So in the same way as arrays and pointers, there are some symbols in C that just are attached to a certain variable type, and that's what the single quotes is. The single quote says the letter A. I can store the letter A in an integer variable type. I can also store the letter A in a character variable type. Generally, we're actually only going to be using the character variable type when we're making arrays of them. When we're using a single character at a time, we will most often use integers, and I'll show you why later. It's because sometimes we need to know if it isn't a valid character. We want to know in what way it isn't a valid character, but we'll talk about that more later. For the moment, you can take my word for it that you'll be okay using an integer and then putting a letter into the integer. And then I can do this printf that says this letter has a certain ASCII value, and we can use the same variable. So that's the interesting thing. We use the same variable, but we say, can you do this as a letter? Can you do this as a number? So this %C is the printf format string. We call these format strings, the % things, that says, read that number, look up on the ASCII table what letter it should be, and then print out that letter. This one says, read that number and print it out as a number. So we can see that the same variable has a number value and has a potential letter value, which means, funnily enough, most of the integers we've been using for all the stuff that we've been doing in our lab exercises and tutorials and everything, if we just put a %C in instead of a %D, we could have actually looked at these things as if they're letters. A lot of our maths wouldn't make any sense in that case. Like, what even is A plus B? You know? So, but knowing this allows you to understand that the variables that we're using to represent letters are nothing more than numbers, which means all of the stuff that we had before that could use numbers can take those letters and do things with it. As in, is one letter equal to another letter? We know that if we ask the question of whether a letter is equal to another, we'll be testing their ASCII values against each other as numbers and saying, are they the same number? Which means we know that all that maths we're doing will still work. We can even do tricky things like, is a letter greater than or less than another letter? And you saw in the ASCII table that things were in alphabetical order, which means that way, if we made sure we were checking only certain regions of the table at a time, we'd be able to see if a letter was before or after another one in the alphabet. So lots of cool little tricks like that. We also have some cool library functions that we can use. Some of these are in standard input-output. One of those is getChar. So getChar is a function that will read a single character from standard input, and it will store it in an integer. The reason why we use integers is that this particular function, getChar, will actually tell us a -1. It will actually return, because this returns an integer, getChar. It will return an integer if we get EOF, end of file, which is that the input was not read correctly. So if it wasn't a character, which is very hard for us to actually type anything in and for it to not be a character, but Control D is that. If we do Control D and say input has ended, then getChar will say my result is -1, and this is why we're using an integer, not the character variable. The character variable actually doesn't have any negatives, so it goes from 0 to 255, so it's not able to deal with this -1 code, which is why usually when we're doing single characters, we will do them as numbers so that we can deal with that. The other thing that's interesting is everything that we type in doesn't immediately go to our program. Usually our terminal will allow us to do all of the things that it's trying to do, and then when we press enter, all of the text that we typed in goes in at once. And so if we ran getChar in a loop, it wouldn't run at all until we press enter, and then it would run multiple times on every letter that we have. I don't really have time for a demo of the code today, but don't worry, we're going to kind of go back over characters on Friday, and I'm going to show you all the demo code then and stuff. But here is some... Actually, maybe we can... What do we got? Oh, we got 7 minutes left. Let's run this code, because this code is really handy to see what's going on. And then I think I will probably not go that much further in this lecture. I know that I've got some slides at the end of this lecture that are copied at the start of the next lecture, so I knew that I was going to end somewhere in here, but I might use this. So what I'm going to do, sneaky, copy everything here from the slides. I mean, I assume people have been doing this every now and then when they've been testing stuff. I also pretty sure I have a characters demo code file. Let me check if I've already got one. Go to WebCMS. Did I put a characters demo in the week 5 lectures? Code, characters demo. Okay, cool. Debug this.c, lecture 9, that's the right place. Okay. we will open the character demo here, and this has some information from the code that was in the slides, but this is the bit that we want to look at. So what I might do is, for the moment, comment out the rest of this so that we can just look at this function here, which is that slide. Okay, so there's other stuff there, which is also in the slides, but what I want to look at is just this here, which is going to say, set up an input character that we can have, ask the person to type in a character, run getChar once, which will take one character from input, and then say that input has this ASCII value. So we will compile this. I'll call it char demo. Should have called it Charizard or something. Okay. Char demo says, please enter a character. So I could enter the character A. The input A has the ASCII value 97. If I want to go back and check the ASCII table, I will probably verify that is correct. Trent's asking, why does it say sometimes? Where did I say sometimes? Was it in this code or was it in the slides? Wait, that's not the slides. Slides are on my computer. Oh, right. This is sometimes getChar won't get its input until enter is pressed at the end of the line. That's a fair point. That it's actually all the time. getChar will never get its input unless we press enter. There's nothing that will send the input from the terminal to the program unless the enter key is pressed. So that's a really good point. I think the only reason I had sometimes put in there is so that people remember that sometimes you get your input, sometimes you don't. But the input is definitely only triggered by the enter key. So I think it's very rare for me to find like a definite change in the slides like that. But that was like a really good pickup there. Okay, so let's go back to my code here and have another look. So there's A. Let's run char demo again, and I'm gonna do something funny. I'm gonna press the spacebar and then press enter. The input, gap, has the ASCII value 32. So now we're getting to the concept that the spacebar is not a gap between words. The spacebar is a legitimate character of its own, and it has an ASCII value. And if we were going to store characters, we can store space like a character. I've got an even better one. I press the enter key instead. The input enter key, and it's like retyped my input, so it's done like the /n is the representation of the enter key, has the ASCII value 10. So the new line, the thing that shifts us down a line in the terminal, is also a character. So we've got these invisible characters that are also still useful for us, and we can store them, which means we can print them back out again. And this is the same as every time we were doing printf, where we had put a space somewhere in our printf. That had a character that was happening. Every time that we put a /n in a printf, and we did that just here with these, we were doing printfs with /n. In fact, I've still got these in here, which I probably want to get. Actually, I'm not going to get rid of them. I will upload this post debugging thing with these still in it so you can see it. But even these, I was using, and it's weird, right? Because I used two key presses here, the / and the n, but when it comes out to here, it'll end up being 1. So there's a symbol here that actually takes 2 letters to type in, but it becomes a single character here, and it has its own ASCII value. So we're getting to the point where like there's a lot of keys on the keyboard, there's a lot of symbols that don't actually have a visible character, but they still have a full purpose, and they exist as a character. Girachan's asking if we can store a click. Not in ASCII, because ASCII it's like, if you want a real old school, ASCII was the 8-bit pieces of information that your keyboard would generate when you press keys, and they would send it to the computer. And the mouse, traditionally, when it was created, was run on a different system than ASCII. So we don't necessarily store click. William's asking what the difference is between puts and print. So there is a here a function called putchar, which is going to put a character onto the terminal, and it actually acts nearly identically to printf, single character, and character. What we're seeing is a bit of a redundancy between things, where printf is capable of doing what putchar can do, but it's generally used for different purposes. So printf is used for printing out long lines of things, whereas putchar says I only do one character at a time, and I'm specific to doing one character at a time. So while printf can do a single character, it also has more capabilities, but putchar only has that one capability. You could nearly think of printf calling the putchar function. So putchar is that function that was running in the character demo. Although the function is not actually running here. We're actually using the printf, but we can do this where we can just print out a single character at a time. They're very, very similar, but putchar only has that one capability. Okay, I should wrap it up there. So we've hit the end. So what did we look at today? Don't worry about all these slides about characters. We're actually, because I've got this kind of overlap, because it depended on how much time I wanted to spend on debugging, how far I'd get into characters. Characters is like, this is your first cliffhanger from 1511. This is a to be continued, and we will talk about this on Friday, and we're going to expand it to strings, and we're going to actually use some, we're going to do some demo code showing all that kind of stuff. But what did we look at today? We looked at some pointers again to make sure we knew what was going on with those. Don't worry too much if pointers are still confusing. We will continue with them. We'll start using them with specific contexts, which hopefully will help you understand them better. But the main thing we were doing today was looking at debugging. So these are the kinds of skills that I think will carry through all the way through your programming career, where you will always be creating bugs in one way or another. We just do. So in, I don't know, how long have I been coding? 25 years or whatever that I've been coding, I still just create bugs. You've seen me do it, where I pretend that I made a mistake to show you something. Sometimes I'm just making a mistake. But again, I still find that valuable. I think it's important for you to know that a great deal of experience with programming doesn't protect you against making mistakes. Knowing how to find them and fix them is much more important than trying to somehow never make a mistake in your code. I think trying to never make a mistake is more likely to cripple you than knowing that the mistakes are inevitable, but knowing that you can fix them is a much better way of doing things. All right, and we also had our introduction of characters, but it's a bit of a to be continued. So on Friday, we'll continue with characters. We will expand them into strings of characters, which is putting characters into arrays, and we'll start using them. All right, thank you, everyone. I will end the official lecture there. And I'll come back in a second. I'll answer any questions people have about what we were doing today. I assume there's probably going to be some questions about characters, but a lot of the questions about characters, don't worry, because characters is a to be continued. You'll be like, what's going to happen after the cliffhanger? He's behind you. All right, see y'all. Alrighty, I'm back. Did we have any? Oh, we had a question there that I saw just before the thank you and goodbye at the end. Cheku is asking what should be typed in the getchar bracket. So, a couple of things that we can do when we see that there is a standard library function that someone's saying, hey, you could use this for stuff. So let me go back to getchar. Was it getchar? Yeah. So we can actually look this up and see what information we can get about this. There's a couple of ways we can do this. One way is I can simply type it in here. Oh, there's actually a really good autocomplete there, which was getchar versus scanf. So someone might have some information there to talk about what the deal is there. So there's a wikibooks here. This tutorials point website is something that a lot of us use for the C standard library. It's like a really good documentation of what is in the C standard library. So C library function getchar. Description: C library function int getchar void gets a character, an unsigned character, from standard in. This is equivalent to get C with standard in as its argument. We don't have to worry too much about the other things. As I said, there are a lot of different possible functions in our standard libraries that we're not necessarily using. So when we get deeper into it, sometimes I'm going to say, I'm just going to teach you this one function that does this, and there's like 8 functions that do the same thing in there. In the same way that we could nearly ignore getchar forever and just use scanf. Scanf is a bit weird though, because scanf sometimes will just try to match the particular string, which means it won't always pick up those invisible characters when it's going for things like words and stuff like that. Or even letters. I think doing scanf with a word is like super dangerous. I wouldn't even bother trying to do that. So getchar void. So we see this void keyword, and remember the void keyword. Oh, this is good. Okay, so Dan is asking, I still don't understand the void meaning, and so that's a good thing because I was just about to talk about it here. Void, and we've been seeing it a lot, right? Because we see it in every single program we're doing. Void is the lack of variable type. One thing that's interesting is if I just did this, I'm going to save this and compile it. Still compiles. Void is the lack of a variable. So sometimes we put it in so that we're really, really clear that there's no variable there. But if we just had no Okay. We're back now. Let me just wait a moment and wait until the stream catches up with me. So as I noticed earlier today, there was something up with my stream, and I'm glad that it wasn't until after the lecture finished that the stream cut out entirely. But I saw it then just drop out entirely. But we're back at our normal bitrate now, so I think there's just something up in my neighborhood at the moment, because it was momentary. Anyway, so things that I was saying, okay, about void. Void is the lack of a variable, or the fact that where there could be a variable, there isn't one being used. So when we see void functions, I wonder if I have a good example. What did we do in lecture 8? Pointers demo? Shuffle definitely have it. Oops. I need to type in gedit properly for that to work. Shuffle.c. Okay. We have these void functions here. If the type of the function is void, that means the function itself does not give us back any information. So when the function runs, shuffle void, I can't store it. I can't store the result in anything because there is no result. It's a void result. If there is a result as opposed to the void, like read input, here I can take the result of read input and I can put it into something. So void functions cannot be made into like int x equals shuffle, because shuffle does not give us back any information. It gives us the empty void instead, which the empty void cannot be stored in a variable. So this can't be done with a void. The other thing that we could do is we could have a function that doesn't have any inputs. This remind me to undo this before I move on. So let's say shuffle had no inputs. I don't understand how the shuffle function works with no inputs, which is why it has inputs. But theoretically, we can have a function that has no outputs and no inputs. We're very limited in what we can do if we have no outputs and no inputs, but it's still technically possible. This and this mean the same thing because the void just says there's nothing here. And so sometimes, depending on the situation, I can literally just say there's nothing there, and then nothing will be there. I've typed too much. I don't know if my Control Z is going to take me back to... Okay, good. I wanted to return this to the state it was supposed to be in. But the int there says, I'm not taking any inputs. And you could be saying, like, how can we give inputs to main? Spoiler alert, that's in Friday's lecture. I haven't finished the slides for that because I'm doing something new. Specifically for this term with the lecture exercise for that, so I'm still going to do that today and tomorrow before it's ready for Friday. So you can't actually look at the slides in advance and see what I mean by that, but we'll get there. So the void says no variable, and so the int does not take a variable's input, the swap does not give a variable back as output. So if we go back to this, we're saying int getchar void says getchar is a function that will give us back an integer. It will not take any input. So they're being very explicit here to say that getchar will not take any input, because what it's going to do is it's going to read what the user types in the terminal, and then it's going to take that value and store it in whatever integer it's asked to store it in. So if we look at my getchar code here, oh, wait. I can't highlight things. That's the one thing about my slides sometimes, that I want to highlight things. But yeah. I can't give any input to getchar, but getchar is going to give me a number back, and I can store that number in this int that I created with which to receive that input. So hopefully that gives you a little bit more information about what's happening with void or not. Void is a keyword that says that nothing's there, which is always a bit weird, right? It's like, this is to signify that there is nothing. I was like, but there's something because it's got a word, but that word means nothing. Okay. Oh, Kat is saying, maybe off topic, but off topic. We're outside the lecture time now. We can ask, well, don't ask me to dictate whether sushi is allowed or not. But way off topic, but if integers and double and characters all have a different number of bits and bytes, does that mean they each have a different length of binary code? You are correct. They do. So the number of bits that each of these variables has is exactly the number of ones and zeros that they store. So in memory, a character is 8 ones and zeros. And if you flick those to all their possible different combinations, there's 256 possible combinations they could be. 256 possible combinations is not enough for numbers, right? Because if we're working with numbers and we only have 256 possible values, that doesn't even count up the number of students in this class. So we've got a simple situation where we can't do that. We can't use it. So we need bigger numbers for that. So that's why we have 32-bit variables for integers. So character, actually, I'm gonna draw this stuff. So let's say I've got my character, and this is a char, 8 bits. Which means I didn't leave myself enough space. I already know I didn't leave myself enough space for this. My wonderful drawing skills here. There's an int that is 32 bits. And I'm not going to do all of this, but if we were to split this up, there'd be zeros and ones like that. That, depending on how my operating system says this is how I store stuff in memory, is going to mean something to us. It's going to be a character. So whether this is the letter B or the enter key or something like that will depend on what number this represents. Binary has a standard way of representing numbers, but if you go deeper into this, it's not always represented exactly like that. So the integer is not necessarily represented just as an integer, because it also has to decide whether a number is positive or negative. So there's more information there. I'm not going to go too deep into that. But there's 32. I'm not going to draw all of them. 32 in here. And then a double. I don't know why I committed to this. But it's 64 bits. So it will be roughly twice the size of that integer. So that means that when these are being used, my computer will read this much memory when we're working with a character, it'll read this much memory when we're working with an integer, and it'll have to read this much memory when we're working with a double. When it comes down to it, that means a double takes 8 times as much memory reading time and memory accessing and stuff like that than a character does. A double is a more complex thing. Character is rarely used on its own anyway, so what we may end up doing is making an array of multiple characters and we deal with a word. So sometimes a word takes just as much or more effort as a double does. Not too worried about that at this stage. In 1511 we're worried about just getting things right and learning how things work. But if you go deeper into this, I don't know how many people are definitely comp sci students here or are going to be continuing into a degree in this. You will pretty soon get into the idea that we don't just want to make stuff work, we want to make it work quickly and we want to make it work efficiently, and then we start taking all these things into account when we're doing things. And you want to get to like super detailed level stuff. We take into account how much memory goes from our RAM to our CPU at a time. Is our memory controller grabbing us 32 bits at a time? If it's always grabbing us 32 bits at a time, then every time we get a single character, we're going to get all this extra data as well. And if it's grabbing us 32 bits at a time, it means it needs to grab it twice to get a double. So this makes the double less efficient than the integer. So then we get those questions and arguments that we have about whether we should use doubles all the time, even to represent integers, because like seemingly there was no cost in having something that had more precision, but the cost might be the fact that it takes more memory. So lots of little details like that. I probably went too far in answering that question, but it is super interesting, right? Because this is a lot of how stuff works actually on the computer underneath where we look at things. So you're saying if a computer knows when to stop reading a line of binary and make that a new character, yeah. So the computer knows that if the variable type was character, then we read exactly 8 bits. So the information that's being stored about a variable isn't just the raw data of the variable, it's also how much of it we can expect. So when we declare this piece of memory of 32 bits that we're going to use as an integer, we give it a name. So we already know that if we've given it a name, somewhere there's more information about this than these 32 bits. So in our program, there's information that when we see that name, we go to this memory location. And also when we see that name, so int a or whatever, for example, or int counter or int I, that will have a memory address for where it is, which is what we can access when we put an AND in front of it. And we'll also say what type it is. And what type it is will say that I can then be used in functions that are also of that type, and I have an exact amount of memory that I will be read, and so I will read these 32 bits and I will not read anything beyond those 32 bits when I'm looking at what the value is for that integer. But I like that what you're asking about there is the depth of, you know, when this comes down to it, when this boils down to it, all these things are just ones and zeros. and how are we treating these things. So we've built these structures on top of the ones and zeros. Going through questions. Most of the questions are about the stream dying. And Dan was asking, what about the void function? So going back to, I don't know if I've already answered this, Dan. I don't know, did I answer that already before I started talking about the bit representation of individual variables? I'm not sure. But a void function like this means that one way we can think about functions is when they get called here, like this function gets called, it will go and jump to here, and it will do everything, and then when it finds a return and a value, and the value is going to be whatever the value of this integer is going to be, this thing will return to this location and will say, I am no longer a function that's going to run. I will now transform into this type, an integer. So after this is finished running, it will turn into an integer value, which is whatever its return was. So this is going to be the number of cards, which is likely to be the number of cards that someone has inputted. But whatever it is, it's going to be this I, and this will transform into an I. Well, into an I. No, transform into a value, which is the I that was in here that can then be stored in this variable here. These functions do not transform into anything. So they perform their function. So shuffle, we get down to here, we do shuffle, it does all of this, and when it gets to the end, I mean, we could nearly say it returns like so. This is actually legal C. I can do this if I want to. And it returns, but there's no variable there, which is why I don't usually put it there. There's no variable, which means it returns nothing. The void function returns nothing. So what actually happens here is after this thing runs, it's like it disappears. So it's like a line of code that runs, and then you simply move on to the next. There is nothing left over here. There's nothing the function is giving back to the other function, whereas read input is giving something back, which is this integer. And then that integer can be stored. Shuffle doesn't give anything back, so it can't be stored, but it still runs, and it takes input and it does something, but it doesn't turn into any information here. And Shrey is pointing out to Kat that COMP1521 goes into a lot of the in-depth detail about bit representation and stuff. And I think you actually get into lower level computing, Shrey, if I'm correct there, and you start working in a language called assembler, which is like, if you take C and you take something simple like A plus B, and you go, how do you actually do A plus B? You can actually program that. You can actually program, okay, we can take the bit representation of A and the bit representation of B. How do we combine them together so they end up adding up? And you actually work through that. Where C, we just assume that something behind the scenes is dealing with that for us. But when we're working assembly, we do it manually ourselves. And you start to learn about, those tiny bits of memory that the CPU has on it. You'll actually use it and stuff. So it's really cool. There's a game called Human Resource Machine that I love talking about because I played it through. And it's got a cool theme to it as well. But you work as this little worker in the building that does these little commands and stuff. And it's actually assembler. It's not the same syntax, but all the commands are exactly assembler commands. So if you want to get a head start on 1521 and play a game about programming, it's called Human Resource Machine. And I'm still wondering about how many sales of that game I have been responsible for because I keep mentioning it in my lectures. So it's been like, I don't know how many thousand students in CSE that I've recommended to play that game. Okay, so Dan's asking a question, and this is a very good question. If a function doesn't give something back, then why do we use the function at all? So let's think about these functions, because we definitely used these, right? PrintDec is one of the easiest void functions to think about. What it does is it reads the deck and the deck size, and it says, I'm going to loop through this and print it out to the user. So it does not give anything back to the main function. The main function also doesn't require anything of it, because the reason why the main function is calling this is it's saying the user wants some information. take this array and this much of it, and please write this out to the terminal. So printdec does that. It has something to offer us. It has a use. It has a good use, because without it, we as humans won't be able to see what's going on. So the main doesn't need it. The main doesn't need any information back, but the user might need some information, which is why it exists and why we run it. So even though it's a void function that doesn't give any output to the program, it's working in a completely different kind of output, which is human output. So it's saying, hey, human, here are the numbers. And shuffle is subtly different, right? Because shuffle is saying, here is a deck and the size of the deck. I'm actually going to go into this deck. So as I was saying before, arrays can be accessed from inside functions. So what shuffle is going to do is it's going to go into that deck and it's going to change the order of the things in the deck. So even though it doesn't tell you anything about what it did, we still know that it did something, and it has a side effect with this variable here that is useful to us. So I don't need to know specific information about what shuffle did, but I know that it affects this variable, and I know that after it's done, this variable will be different. So the void doesn't mean that it doesn't do anything. It just means that it doesn't give us back that specific single variable worth of information. Instead, what shuffle does is it changes what's in this variable, and then when it's finished, I know that I can then use that variable for something else because of the side effects of what shuffle did. So I think that's like that should give you a bit more of some information about a void function is not useless just because it doesn't give an output. It may have other effects. So printdec is really obvious what effects it has. Shuffle's also reasonably obvious. It's going to take that array variable and it's going to make changes to it, because when we pass arrays into functions, the array actually gets access to this variable. It's not necessarily going to make a new one. So the deck size it won't be able to change, because that's just a normal variable. But because this deck that is passed into shuffle is the address of the piece of memory where this array is stored, then shuffle gets access to that and can make changes. I hope that's helping, Dan. I hope we've given you a bit more of an insight into what's going on. If you're still having problems with this, you can talk to your tutor about it this week, or you can even go along to a help session and talk to them about, okay, I've seen a bit of the difference between void functions and non-void functions, but I'm still a bit confused. And even if you're like using some of them in your assignment or something like that, you can bring that into a help session and talk to someone about it and just go, look, there's some of the fundamentals going on here that I need to learn a bit more about. And so sometimes you may be able to see this from someone else's perspective, not just mine. And then it's often really great when you get that second perspective. Things might start to click, but see how you go. All right, I should wrap it up there, everyone. Thank you for coming along, because I think that the questions have stopped coming through now. And my throat is telling me that I've been speaking for 2.5 hours and I should stop. Okay, thank you all. I will see you on Friday. On Friday, we will continue the work that we were doing on characters, expand them into strings, and we'll have a whole demo about how we use them there as well. Okay, goodbye all.